Now let's make another pass looking at the particular regions of operation, and I'll give you a bit more information. In the ion chamber region, the output signal is proportional to the amount of charge deposited in the sensitive volume, that is, in turn, proportional to the incident particle energy. In principle, this could be used to identify the type of particle and its energy, but the signal is not large, and only strongly ionizing particles, for example, alpha proton fission fragments or heavy ions, are detected. For typical ion chambers, only particles with energies of 10 keV and greater are detected. Ion chambers come in two basic designs: pulse counting ion chambers and integrating ionization chambers. The first, the pulses and their height are tallied electronically, and in the latter case, the current itself is monitored. Most ion chambers are cylindrical, but some use parallel plates, and some use a combination to help detect alphas and betas while still doing a good job with photons. Most ion chambers use air as the counting gas. It's cheap and it's readily available. There is often a window for alpha and beta so that these particles can more easily get into the sensitive volume of the detector. A piece of paper stops an alpha particle, and a few millimeters of aluminum stops most beta particles. If I add boron to the sensitive volume, then neutrons interact with this boron and create charged particles. These detectors can be used to monitor neutron fluence rates at a reactor, for example. There are several design paths to minimize the interference of gamma rays with these detectors, including decreasing the amount of chamber gas or increasing the amount of boron, among other ways. We'll talk about it more in a minute. With proportional counters, we can identify the type of particle, whether it's alpha, beta, or gamma, and its energy. For the counting gases, helium or argon for alpha, beta, and gamma, or boron trifluoride for neutrons are the most common. Detection of low-energy particles below 10 keV is possible due to the gas amplification. To stop a Geiger-Müller discharge, a quenching gas, often methane, is added to the counting gas. This helps resolution but limits the lifetime of proportional counters for all except gas flow counters. Geiger-Müller counters work in the GM region, where the number of electrons produced is independent of the applied voltage above the GM threshold, and the number of electrons produced in the gas is independent of the number of electrons produced in the initial radiation. Identification of the type of radiation, the number of original ion pairs, is impossible. Therefore, the only information is about the number of particles. The GM detector would discharge continuously after the first pulse, except by positive ions around the central anode wire form a sheath around the wire, reducing the apparent field strength. Also, a quench gas is normally added. Halogens can be used, and they have the advantage of recombining later in the tube. Other quench gases can be used, but if they don't reform after use, then they limit the tube lifetime due to degradation of the fill gas. GM counters are limited to low count rates due to the large dead time for each count. Again, we'll talk about this in a minute. Despite these limitations, GMs are widely used to look for contamination or to guard against the release of radioactive material because they are sensitive, portable, they have simple counting circuits, and the ability to detect very low levels of radiation.